All right, so we've seen how in carbon NMR we can use chemical shift to tell us about the environment of the carbons. In proton NMR we can use proton chemical shift, the shift of nuclei, to tell us about the environment of hydrogen atoms in a molecule. So we can measure we can determine information about two of the most important nuclei in organic or atoms in organic chemistry, because almost everything has carbon and hydrogen in it. Right? It's more difficult to do NMR on other interesting elements. In principle, you should be able to do it on nitrogen, oxygen, but for technical reasons, those are very difficult to do. So we don't necessarily gain information so much on functional groups directly as we might in infrared. In infrared, we learned that we're directly measuring, looking at whether a compound has OH bonds, carbonyl, C double bond O. Those are the two main things that we learn about. In NMR, we're not really looking at the oxygen at all in the carbonyl group, but we recognize that we can see indirectly the presence of a carbonyl because carbon-13 nuclei with doubly bonded to oxygen have chemical shifts that are characteristic, 175 to 200 ppm, depending on whether you have an ester, amide, ketone, and so on. But we can indirectly determine the presence of a carbonyl group. So proton NMR helps us learn about the types of protons in a molecule. And in proton NMR, once more, not only do we learn about the environment of the protons, but we can do integration so that we can find out how many protons there are in a certain environment. So if we see a signal that integrates for 3 hydrogens, that suggests that are all in therefore identical environments, that suggests a CH3 or methyl group. Right? Methylene groups generally in many organic compounds, the 2 hydrogens in a methylene group are homotopic, same chemical shift. And so we see a signal that integrates for 2 hydrogens. So we can pretty much count the hydrogens out in a proton NMR. So we're learning a lot about molecular structure. So at the end of looking at the chemical shift and looking at the integration of proton NMR signals, we can pretty much say that our unknown molecule has 5 methyl groups, 4 methylenes, and 3 methynes, for example. The problem, however, is connectivity. So in determining a structure, we don't just need to know the sort of information it's got 5 methyl groups, but we want to know what those methyl groups are connected to, what the connectivity pattern is a methyl group connected to a CH, or is it connected to a CH2, for example? Or is it connected to a quaternary carbon where there are no hydrogens on the neighboring carbons? And we can't really get that connectivity information from carbon NMR. Carbon NMR tells us about the carbons, but it doesn't tell you anything about this carbon is connected to that carbon, right? And proton NMR, chemical shifts and integration don't tell us where, they tell us the total number of methylenes and methynes and so on, but we don't get the connectivity. So, in fact, to get the connectivity is really the most important thing to finish the structure, right? We work our way through. We start with information like mass spectrometry tells us the molecular weight. Carbon NMR tells us the number of carbons that we might have in the molecule. Proton NMR, the number of hydrogens. And we can work our way towards a molecular formula. So molecular formula is more specific than molecular weight, and we've got some degree towards solving the structure. And we can begin to put in work out whether we have some functional groups, and so on and so forth from infrared. But we really don't need a way to put all the pieces together. And in fact, proton NMR, the third aspect of proton NMR, the so-called multiplicity that is introduced on slide 31 of chapter 16, begins to tell us the connectivity between the pieces. So I've shown you some proton NMR spectra last week, and we noticed that we said there were, for example, in ethyl benzene, right, there were aromatic protons with an aromatic chemical shift of 7 ppm. methylene protons, a CH2 group which integrated for 2 protons, and a CH3 group that integrated for 3. But you noticed in those spectra that there was not just one single signal for the methyl group, but that it was actually split into 3 signals that had the sort of ratio 1 to the 1. So this sort of signal, this is the methyl group of ethyl benzene, looks something like that. Okay, and all the hydrogens are equivalent. This is not saying that there are 3 different hydrogens in a methyl group. There are. But in fact, this splitting, this fine splitting bit of the peak, tells us not about how many hydrogens there are in the methyl group, but how many hydrogens there are on the carbon next door. In ethyl benzene, there are actually 2 hydrogens on the carbon next door. And from NMR, I can determine that because I see this ratio of peaks. This is called a triplet. The signal is divided into 3 by the presence of 2 protons on the carbon next door to the methyl group that I'm looking at. And so we see these so-called splitting patterns. And the first slide shows you a variety of these. A single line means that there are no neighbors next door, and we call that a singlet. 2 peaks result from 1 hydrogen on the carbon next door to our methyl group, or whatever it may be. We call that a doublet, triplet, quartet, quintet, sextet, and septet, so on. Okay, and we can get into very complicated splitting patterns, but these are the basic sort of set of patterns, and these result from coupling to an appropriate number of equivalent neighboring hydrogens. So if we look at 2 non-equivalent hydrogens on 2 carbons next to each other, as shown in slide 32, we have HA and HB, one in red, one in blue. They're different environments, and multiplicity results from the effect that the magnetic field on HB has on HA. So we talked about how NMR was all to do with magnetic billiards, right? We're going to put nuclei are spinning, we put them in a magnetic field, they align with or without or opposed to the magnetic field, okay? And then the energy gap depends on the spin of the electrons that are surrounding the nucleus, the shielding, de-shielding effect. But now we see that the actual magnetic field felt at nucleus HA also depends to some extent on the spin state of HB. So HB has 2 options. HB can be up, aligned with the field. So if HB is spinning up, aligned with the field, that a little bit of that magnetic field created by HB is felt over at the nucleus HA. If, on the other hand, HB is aligned against the field, that reduces the field felt over at HA. Okay? It's a pretty small effect, as you might imagine. These 2 nuclei are not all that close to one another on average in most molecules. And so the little small tiny magnetic field created by the one nucleus spreads out through space, but eventually is felt by the nucleus next door. So HB can be aligned with or against the magnetic field. So some HB atoms, HB atoms in one type of molecule will be aligned with the field, and HB in the other type of molecule will be aligned against it. What are the odds of it being aligned with or against? And we pointed out last time that NMR is a very insensitive technique. 50.001% are aligned with the field of all molecules, and 49.999% are aligned against. So it's a crapshoot. If I'm sitting on HA in one molecule, I have a 50-50 chance of HB being aligned with or against the field, but it's aligned one way or the other. It's quantized. So HB has to be either up or down. It can't be anywhere in between. And so in one particular molecule, HA will feel the magnetic field reinforced by HB. And in another molecule, it will feel a lesser magnetic field and it will resonate at a different frequency. So the end result is that magnetization gets transferred from HB to HA. HA, half the molecules, here's the chemical shift of HA if it were a singlet, half the molecules are shifted slightly one way and the other half shifted slightly the other way. So we see a signal called a doublet, 2 peaks instead of 1, okay, centered around the true chemical shift. So HA only has 1 chemical shift. This is not a difference in chemical shift. This multiplicity is something else. It's caused by the number of protons next door. Okay, so in slide 33, we see that HA appears as a doublet because there is 1 neighboring proton. And so the corollary of this, what's important to know, is not why HA splits into a doublet. What's useful here is to ask the question, what do I know if I see a doublet? So let's say I see some peak. It's a doublet. What can I deduce from that? There must be 1 hydrogen next door, right? Because something has split that peak into 2. So by looking at the coupling patterns of proton HA, right, we can still integrate here. We can integrate the doublet. The area under the peak is the same. It still corresponds to 1 proton. So we've got information on the environment of HA from its chemical shift and of HB. We've got information on the number of HA protons. By looking at the multiplicity of the peak, the number of signals in the fine splitting, we also get information on the number of neighbors next door. Note that that's independent information. I can have a 3-proton methyl group with 1 neighbor. That would be a doublet. I can have a 2-proton methylene group with 1 neighbor. That would still be a doublet. And I can have a 1-proton methine group with 1 neighbor, and it's still a doublet. It's got nothing to do with how many hydrogens are on the carbon at the site that I'm sitting on. It's got to do with how many neighbors I have. And that is key information because that enables you to begin to put the little structural pieces together. It tells you, for example, that I've got 3 methyl groups in the compound, 2 singlets and a doublet. So the 2 singlets must be attached to a carbon bearing no neighbors, while the doublet results from being a methyl group being attached to a carbon bearing 1 hydrogen. Okay? And so we can then go to that carbon bearing the 1 hydrogen and we can say, well, what's its chemical shift? That tells us about its functionality, functional groups. Okay? And we can begin to piece the whole structure together by looking at multiplicity, by understanding not the number of protons at a site, but the number of protons at the neighboring site. Okay. 2 protons on the adjacent carbon. Here we go. HA. I sit at HA, and I have 2 neighbors. So what are the possibilities? In some molecules, both the neighbors are up. In some molecules, both are down. Then there's up, down. And there's also down, up. There are 4 possible permutations. Right? Yeah? Okay. So, 2 spins reinforcing. That's one possibility. The odds of a molecule having both spins up is 1 in 4, right? Both spins down, that's the other possibility. That makes the line on the other side, on the far side of this so-called triplet. The line in the middle of a triplet corresponds to 1 up, 1 down, but there are 2 ways to do that. There's up, down, and down, up. It's like flipping a coin, right? You flip a coin twice, you can get 2 heads, you can get 2 tails. You can get a tail and a head, or you can get a head and a tail. And a tail and a head and a head and a tail are not the same thing. The odds of getting 2 heads is 1 in 4. The odds of getting 2 tails is 1 in 4. Head and the tail is 1 and 2, right? In any order. And in this case, because the two HB protons are equivalent to one another, so they will both act equally on HA, up, down, and down, up have the same energy. So we generate, and this is purely statistics really, we generate a triplet, 3 possible permutations. The one in the middle, up and down, or down and up, that is the chemical shift of your protons at that particular site, the center of the multiplicity. But we have signals that are shifted one way or the other way, or not at all, because up and down cancel out. HA stays at its chemical shift for the middle line. So there's a 1 to 2 to 1 possibility here, right? The center line is twice as big as the outside lines, because there's only a 1 in 4 chance of a molecule having both up, a 1 in 4 of having both down, but up, down, and down, up are identical to one another. They add up in the middle to make a 1 to 2 to 1 set of lines. So we see these absolutely classical patterns. One of the reasons that we know that this sort of signal is not due to 3 separate protons at 3 separate chemical shifts is that the separation of these lines is equal all the way through the pattern. It has to be that way. So if we see this sort of signal, the corollary, the important point is this. If I see a resonance and it's a triplet, how many neighbors must we draw in the structure? 2, right? The only structures that are acceptable for a methyl group that is showing up as a triplet are ones that have 2 hydrogens on the carbon atom next door. Yeah. Exactly the same as long as the hydrogens are identical. If in the case that the hydrogens are not identical, the size of the splitting may be different. So then you get what's called a doublet of doublets, right? The one hydrogen has a big splitting. The second hydrogen gives you a small splitting that works on both sides. See, 1 to 1 to 1 to 1, doublet of doublets. Okay? But we will get to those more complex splitting patterns later. All right? So let's deal with molecules where all the hydrogens are equivalent for now. Okay. Half of the HA, okay, 35, we've said. 36, we've said. We've talked about the integration ratio, 1 to 2 to 1. Okay, so let's move to 37, and now here we're now going to look at what happens when we have 3 neighbors. And especially in the absence of any slides, this is kind of hard to explain. I'm going to let you largely walk through it, right? There are now, in fact, 8 permutations. Up, up, up. Easy to understand. Probability is 1 in 8, like 3 heads in a row flipping a coin. Down, down, down. Same thing, 1 in 8. Then there's 2 ups and 1 down. There's 3 combos for that. And then there's 2 downs and 1 up. There are 3 combos for that. So this is pure statistics, yeah? If you don't see this, get a coin out, start flipping it, right? If necessary, in the final exam, I will add an extra line saying students are also allowed coins, okay? On top of the model kits, which, by the way, you are allowed in clear plastic bags while we're dealing with this, right? And the Casio FX991 calculator that everybody clutches going into the test. All right. So we get a 1 to 3 to 3 to 1 quartet. And slide 38 shows you what a quartet looks like. In fact, we can continue this process. You can make a little table. Number of neighbors, multiplicity, relative intensities. 1 neighbor, doublet, 1 to 1. 2 neighbors, triplet, 1 to 2 to 1. 3 neighbors, quartet, 1 to 3 to 3 to 1. And so on. And you're going to ask me, do we need to memorize that table? And the answer is no. Because in fact, you can work out any number in that table very easily. That table actually follows a mathematical thing called Pascal's triangle. In Pascal's triangle, you have a 1 at the top. You have 1s running all the way down the outsides. And every number is the sum of the number just above to the left and just above to the right. Okay? Why it follows Pascal's triangle needn't concern us. But it does, so that in fact, you can write down Pascal's triangle and you can work out the multiplicity pattern of just about anything. So a septet is 1 to 6 to 15 to 20 to 15 to 6 to 1. Okay? And if I had 7 neighbors that were splitting me, I would have an octet, and I could work out immediately the relative intensities of that octet. It would be 1 to 7 to 21 to 35 to 35 to 21 to 7 to 1. Yeah? Following Pascal's triangle. Okay? Is that clear? All right. So, good news. We don't have to remember the multiplicity pattern. So, you can determine the number of neighbors by using essentially the n plus 1 rule. Although I think it's easier, really, to know Pascal's triangle, because Pascal's triangle is very easy to understand. Okay? And from that, you can deduce the number of neighbors. So, 2 signals. Multiplicity is 2. 2 lines, we have 1 neighbor. 3 lines, we have 2 neighbors. Okay? And I would prefer you thought about it that way, because really what we're doing here mostly is applying this rule. We're looking at a spectrum and saying we've got 7 lines. How many neighbors do we have? Right? We don't usually care about it the other way around. That's the theory. Much more useful to sort of think about the n minus 1 rule, if you like. Measure the number of peaks and work out the number of neighbors. So any structure that you draw must be consistent with that number of neighbors. So, there are some key rules here. My goodness. How many neighbors have you got, sir? All right. Equivalent protons cannot split one another. You don't want to know why that is. We have to go deep into quantum stuff to do that. Anybody want to know, now that I've told you that? No. Better not to know. But it's important to recognize that for various reasons. So, for example, the 3 protons of a methyl group all come at the same chemical shift. If there's no neighbors, it's a singlet. Even though you might think that if you sit on one of the hydrogens of a methyl group, you've got 2 neighbors that could be up, down, whatever. It turns out that fortuitously all that stuff cancels out, so the hydrogens within a methyl group do not couple to each other. Not going to say anything further, it's just one of the rules. Predict the splitting patterns observed for 1,2-dichloroethane. Okay, that compound will give you a single line. All 4 hydrogens in that 1,2-dichloroethane molecule are equivalent to one another, right? The 2 in the 1-methylene group are equivalent to one another, and the 2 in the other methylene group are equivalent to the 2 in the first methylene. So all 4 protons are in the same environment, they have the same chemical shift, and they do not couple to each other. So that compound would give you a single line because effectively all 4 hydrogens are equivalent. There's another rule, and that is that because the splitting effect actually happens through chemical bonds. It's not a through space effect. It's not how close the hydrogens are to one another. It happens because all these little magnetic fields influence each other. The field of the thing that you're coupling to alters the field of the electrons in the bond. That alters the field of the electrons in the bond next door, and it all happens through bonds. So, in order to get a splitting, protons have to be within 2 or 3 bond distance. This is why we talk about neighbors. If you look at the example on slide 1641, geminal protons, 2 protons on the same carbon, if they're non-equivalent, will split each other. And this need not concern you too much yet, right? Because we're learning about compounds where CH2 groups always have equivalent protons. But this goes back to the whole issue of homotopic and enantiotopic, and we'll come back and look at that after we've done chapter 5. Vicinal hydrogens on adjacent carbon. They are 3 bonds apart. We can count the bonds, 1, 2, 3. 3 bond couplings are fine. Those are the ones that we usually observe. They're the ones that tell us how many neighbors we have between 2 carbon atoms that are joined together. Okay? That's the most useful information, the only one that need concern you right now. 2 hydrogens that are 4 bonds apart are generally too far apart to split each other. There are some exceptions to that, but we're not concerned here with exceptions. We're concerned with just learning the basic rules. Okay? So you really are measuring neighbors because you don't see an interaction between a hydrogen on 1 carbon and a hydrogen 2 carbons away. That is possibly largely fortuitous, but it's extremely useful. Because if every hydrogen in a very complicated organic molecule coupled to every other one, everything would be a nightmare, right? The technique would be useless. The fact that you can tell in coupling patterns simply about the number of hydrogens on the neighbor next door is extremely useful. The n+1 rule technically only applies to protons that are all equivalent. So the proton shown below will be more complicated than a simple triplet. So the compound on slide 1642, that hydrogen that's in red has a neighbor to the left attached to the hydroxy group, a neighbor to the right attached to the double bond. In general, the influence, the effect of one on the other will be different. What we call the coupling constant will be different, the magnitude of the effect. So in that case, we would have a situation called a doublet of doublets. The 1 proton would split the red guy into a doublet. The other proton would split each of those lines further into a doublet, but not by an equivalent amount. In 2O-A3-B3, we don't do coupling constants. But in fact, the only thing that you really should know is that coupling constants, if we measure them, tell us about geometry. Suppose you have an alkene. It could be cis or trans, right? 2 protons next door to each other. It turns out that the magnitude of the effect of the protons one on another is less in the cis situation, where the 2 hydrogens are on the same side of the alkene, as it is in the trans. Trans coupling constants are bigger. And once you know that, you now have a way to tell from coupling constants geometry. Is it cis or trans in an alkene? You can tell things about geometry in rings that way. So coupling constants, the size of this effect, are the 4th piece of separate information that we get from NMR. So let's quickly review the information. Chemical shift, we have a chart of that. Tells us about the environment of the hydrogens, the functional groups that are attached. Integration tells us the number of hydrogens in that particular group. Multiplicity tells us the number of hydrogens in the neighboring group. And coupling constant tells us about the relationship of the hydrogens one to another, tells us about molecular shape, molecular geometry. But that is all we'll say at this point about coupling constants. So slide 1643 tells you to predict the splitting patterns for all of the protons in the molecule below. UG, okay. I will post the answers to all these later tonight or tomorrow. So this talks about coupling constants on slide 1644. One of the important things, one more thing that you should know, is that HA affects HB to the same extent that HB affects HA. So the magnitude of the coupling constant, there's reciprocity. If something is split by a certain amount into a triplet by a neighboring proton, then that neighboring proton will be split to the same extent by the one that you came from in the first place. Does that make sense? Right. So you're getting connections in both directions, and that's the key point. So if you look at slide 1644, there's a classic example of an ethyl group, right? We have typical patterns not only for one neighbor, two neighbors, three neighbors, but we actually get very classical sort of very characteristic patterns for particular types of groups. An ethyl group has a CH3 with two neighbors. It's a triplet. It has a CH2 with three neighbors. It's a quartet. That combination of a triplet for the methyl group, integrating for three H's, so it's a 3H methyl group, and a quartet integrating for two H's. Absolutely characteristic of an ethyl group. So you've got connectivity information from the couple that you didn't have before. Chemical shift only told you that you had a methyl and a methylene. It didn't tell you that they were next to each other. Coupling, now you know. And so we can now write the structure down. So ethyl groups, typical patterns, there we are, and this tells you why we want to go to bigger, better magnetic fields, but we still see a triplet and a quartet. So there's the ethyl group. Notice that the one at the bottom of 1646 is not an ethyl, because we don't have even splitting in that case. Those two signals, while one is a triplet and one is a quartet, they're not next to each other because we don't have this reciprocity of coupling. Okay, so here is a tertiary butyl group, carbon with three methyls on it. Here all 9 hydrogens are equivalent. We're on 1647 now, sorry. So 3 hydrogens in one methyl group are equivalent, but that methyl group is equivalent to the next methyl is equivalent to the third methyl, right? 9 hydrogens. The carbon to which the methyls are attached has no hydrogens on it. It's a quaternary carbon. So those methyl groups have no neighbors. That gives rise to a 9-hydrogen singlet. You see a single peak for a total of 9 hydrogens integration. That is very indicative of a tertiary butyl. And you will get more familiar with these sorts of patterns through practice. Isopropyl group, 2 methyl groups attached to a carbon with 1 hydrogen. The methyl groups are total 6 hydrogens, right? They're equivalent to one another, so the 2 methyl groups are equivalent. They both have, every hydrogen has 1 neighbor. Every hydrogen is split into a doublet, so we see a 6H doublet. If we look at the hydrogen on the central carbon, it now has 6 neighbors, right? The hydrogen on the carbon in the middle has 6 equivalent neighboring hydrogens in the 2 methyls. 6 neighboring hydrogens, how many lines? 7 lines, right? N plus 1 rule if you use it that way around, right? So you see a 7-line, a septet, and there it is, beautifully displayed on the overhead projector. Not. Right. Okay. Real molecules. There we go. Real molecules are hell. Right? So here is an example where we see a quartet of triplets, right? But in real life, once you have some practice, you could look at this quartet of triplets, and you could say, right, that complicated-looking signal, first of all, there's a quartet character to it. So there's 3 neighbors in one direction to give you a quartet. Then there's a triplet character to each of those lines. So how many neighbors in the other direction? 2, right? So you're sitting on a carbon. You've got a certain number of hydrogens. You can measure that by integration. 2 neighbors to one side, 3 neighbors to the other side. You've got a methyl, CH2, CH2, that's a proton. So we get into more and more complex splittings in real life, but mercifully for you, we won't give you anything quite that hideous. Okay, so that's that, right? And so we're at slide 1651 that says that, you know, you predict the splitting patterns for S-pentenol, and there's the answer. Occasionally we don't see splitting, okay? And we don't see splitting sometimes with exchangeable protons. So here is an alcohol, ethanol, which you might need after tonight's lecture, sitting there staring at a blank screen for 3 hours. You have my deepest sympathy for that. Thank you for your patience. So in this alcohol that you can see so clearly on the screen, there is an OH proton, right? And OH protons can exchange. They can hop from one molecule to the other, right, in an alcohol, just like protons hop from one molecule to another in water. So in this case, we do not see splitting. And the reason being that the proton on the OH group is hopping from molecule to molecule. So I might start with an ethanol molecule with the OH proton spin up, but a fraction of a second later, I've changed that to a different proton that's now spin down. So what is happening at the OH proton is that it's migrating from molecule to molecule. So if I sit on a particular molecule, the OH proton spin is up, down, up, down, up, down, up, down. And if that is happening fast enough, and I'm not sure I can do it in my dosage, right, it eventually just becomes a blur. And under those circumstances where the exchange rate is very fast compared to the time scale of the NMR experiment, which is on the order of milliseconds, then we lose that coupling information. So OH protons, NH protons, exchangeable protons that can hydrogen bond, that sort of hydrogen that can move from molecule to molecule, are more complex, and sometimes we don't see splitting. So there's the spectrum of ethanol. You see that the CH2 group of ethanol is split into a perfect quartet there, coupled to the CH3 protons. Remember that the protons in a methyl group, the protons in the methylene group, those can't hop from molecule to molecule. It's only the ones that can hydrogen bond and exchange, the ones like water, the ones like ammonia, the ones on amines and amides, those ones can exchange. So 1653 sort of says that. Sometimes if you get a very pure alcohol, you can see it, but that just confuses the issue. And aldehyde protons sometimes appear as a singlet, but let's not even worry about that. So here is, so slide 1654 shows you this exchange phenomenon, right? How in the trace of an acid, we can protonate the alcohol. We talked about this. H3O plus is almost as strong as an acid as a protonated alcohol, so we can form an equilibrium. A little bit of catalytic acid protonates the alcohol, and then the other proton falls off, and the net result is that we can change the spin of the OH proton, and that gets rid of the coupling. Okay, another case where OH protons pose a problem is if we use a solvent which can exchange. So if I take an alcohol in deuterated chloroform, that's the solvent that we talked about in terms of how you make an NMR spectrum. Deuterated chloroform, the deuterium never comes off the chloroform molecules. It's a CD bond, it's strong, doesn't exchange. But if I take an alcohol in D2O, heavy water, deuterated water, that you can use as a solvent for polar organic compounds, indeed, it's the solvent that we would use if we were going to study a protein or a nucleic acid by NMR. Okay, and we can look at very large biomolecules these days using NMR as well. That's what makes it interesting. So under those circumstances, if I dissolve in D2O, deuterium exchanges for hydrogen on the OH of alcohols, the NH of amides, the NH2 of amines. through the same mechanism. If you run that mechanism through and change one of the hydrogens to D, you will be able to show that you can exchange the OH proton of an alcohol for an OD group, a deuterium group. And deuterium is the heavy isotope of hydrogen. It actually is NMR active, but it resonates at a very different frequency. So you have to retune your NMR machine to a special frequency to do deuterium NMR. So the reason that we use deuterated solvents in NMR is that the deuterium doesn't show up in the proton NMR ratio. So if I exchange the OH proton of an alcohol for an OD, then that ceases to show up, at least in the proton NMR. So predict the chemical shift integration and splitting patterns for all of the protons in the following molecule. Let's not do that. Draw a spectrum for the molecule. It's always a good idea to draw a spectrum. Over the years of teaching a large second-year organic course, I have learned that asking students to draw the spectrum of molecule X is agony to mark, okay? So simply because of that, not because I don't think it's a good question or it's a good skill to have to go backwards and predict a spectrum. You should try it because you will learn from that exercise. But we do not ask you to do that. We won't ask you to draw something in a test because, quite honestly, the results in some cases can be pretty hideous, and it's no fun to mark. Okay, so here is an example of how we can use the coupling. We're on slide 1657. We're closing in towards the end here. These three compounds are isomers. They're isomers of xylene, dimethylbenzene. So you can have two methyl groups on adjacent carbon atoms, two methyl groups on opposing carbon atoms, or the one in the middle where the two methyl groups are separated by one. NMR will tell us which of the xylenes we have. If you look at the first left-hand structure, look at the blue hydrogens. They have one neighbor, the yellow hydrogen. So the two blue hydrogens are equivalent by symmetry. So we'll see one signal for the blue hydrogens, that is a doublet. And look at the yellow hydrogens. They look like they have two neighbors, except for the fact that the two yellow hydrogens are equivalent. They have the same chemical shift, so they don't couple to one another. So in the first isomer there, we would see two doublets, one for the blue, one for the yellow. One in the middle, we would see three separate proton resonances. The hydrogen between the two methyl groups has no neighbors. What multiplicity do we get if we have no neighbors? Singlet. One line for the green hydrogen there. The blue hydrogens, there's a pair of them that are equivalent. So that would integrate the two protons, and they would both be doublets. And the yellow hydrogen at the bottom has two equivalent blue neighbors, so it's a triplet. So you see the pattern in these two isomers, the pattern of the proton NMR is very different. In the third compound, how many signals should I see for the blue hydrogen? So, all four blue hydrogens are equivalent to one another by symmetry. Right? Identical hydrogens don't couple. So that third isomer gives you just one line for all four blue hydrogens in the NMR. So we have a way, through coupling, to distinguish the different possible isomers in a benzene molecule. And you'll come back and talk about how ortho, meta, and para are used to describe these three different isomers in chapter 17 in 2OB3. Explain how proton NMR can be used to distinguish between the two molecules below. I will leave that as an exercise and I'll post the answer. Okay, so let's just wind up what is important here. Analyzing a proton NMR spectrum is important. Okay, so this gives you sort of some rules, some steps for the process of analyzing a proton NMR. I will help you in the test. Okay, so the test on Tuesday night gives you some spectra, and it asks you to determine the structure. Part A asks you to give the final answer. The reason that we do that is that if your answer to part A is correct, we'll just give you full marks for the whole question. We won't mark all the reasoning. Okay? Because if you get the right structure, hell, your reasoning must be right. Or at least we'll give you the benefit of the doubt. Because we don't want to read through all the reasoning bits if you've got the right structure. So part A says give the final structure. Don't start there. Start by working your way through the reasoning. The reasoning says somewhere along the way deduce a molecular formula, right? We've talked about that before, right? So how do we do that? We work out what the number of carbons are, the number of hydrogens. We can work out the difference. That tells us about oxygens and nitrogens. If you've got a halogen, you know that from the mass spec, chlorine, bromine. And that's about it. Okay? So work your way through following those questions. I guarantee you that in neither this test nor the final exam will I put in any misleading parts to that line of logic. Okay, I will not try to make you stray from the path of righteousness that gets you to the correct structure. Okay? So they're there to help you. The reasoning bits are there to help you. You don't have to do it that way, right? There are other ways too. There is always overkill information in these problems. There is so much information that you really, well, I was going to say can't get it wrong, but let's be realistic. So, work at it, but follow through that sequence of, working through towards the molecular formula. How many degrees of unsaturation do you have, right? Because that tells you about double bonds and rings, right? Yeah? So any structure you draw must have the appropriate number of double bonds and rings. Okay? If you want to know, let's say there's one double bond in the compound, right? Well, let's say there's one index of hydrogen deficiency, right? So what are the possibilities? You can have a carbon-carbon double bond. That's an alkene. 2 sp2 hybridized carbons. So you have sp2 hybridized carbon. You should see that in the carbon-13 NMR. Right? You could have a ring. If you have a ring for 1 degree of unsaturation, there are no sp2 hybridized carbons. So if it's a ring, there should be no signals in the carbon NMR above 100 ppm. You could have a CO double bond. That would be cool, right? Because CO double bonds stretch in the infrared, right? So you could look at the infrared and decide that, yes, you have a ketone, for example. There's your 1 degree of unsaturation. So you then can't have any more double bonds or any rings, and so on, okay? So it's all working through applying logic. There is no single sequence that you have to follow, but basically calculating the index of deficiency, the number of NMR signals, looking for symmetry, analyze each trigger signal, draw the molecular fragments, okay, that's the methyl groups and the methylenes, and then in general, although you don't need to do this for Tuesday, you could apply the coupling rules so that you can work out what fragments must be next to each other. And work your way down the chain. Start at the end, work your way down the chain. The methyls collected to the methylene, the methylenes collected to the methine, and so on, okay? And have fun solving these structures. All right, so we've got one example here. If you want to go ahead. We've got 4 minutes, but I'm quite happy to spend the time running through this one example. Okay, if that's a useful exercise. I know some of you have to catch the bus. And you won't be able to see this fascinating thing on the podcast because there won't be a podcast. Okay, so here we go. We're actually told a formula here, so we'll skip over all the mass spec bit where you count the carbons and you work out the molecular formula, right? We've sort of talked about that. So we've got a compound C7H13Cl, okay, and we have some proton NMR data delta 5.3, there's a doublet of quartets, 1H. Should we start with the fact that it's a doublet of quartets? You actually could. You could start with the multiplicity and work the problem, but it's probably not the best way to do it. So if we follow the rules, calculate the hydrogen deficiency index, and here on this slide they show you the dreaded formula for that. Okay? If you want, you can also remember that that Cl counts like a hydrogen, right? It's got one bond to a carbon. So we can replace that with a hydrogen and say that this is equivalent to C7H14. If I take a fully saturated alkane, that's C7H16. So C7H14 must have 1 degree of unsaturation. Right? That avoids going through the formula, but if you care to apply the formula, by all means do. It'll get you the same result. Okay. So consider the number of NMR signals and integration to look for symmetry in the molecule. And that here is fairly obvious, because if you look at that signal at 1.0 ppm, it says singlet 6H. Well, you can't have 6 hydrogens on 1 carbon, right? Not even the guy who misrepresented the octet rule put 6 hydrogens on a carbon. Okay? So you can't have that. So what do you think? How do you think we get one signal with 6 hydrogens on it? Yeah. That's a good idea. Benzene would give you one signal with 6 hydrogens. But here we're not at the chemical shift of benzene. Anybody? Yeah. 2 identical methyl groups, right? That gives you 6 hydrogens. Yeah? 2 identical methylenes will give you 4, right? So you can have more than 3 neighbors. Okay, so we've got 2 identical methyl groups at 1 ppm. So, at 1 ppm, can we have a heteroatom next to that? No, right? So those methyl groups, therefore, must be attached to the carbon atom. We can't have a heteroatom, right? You can't have 2 methyl groups attached to 1 chlorine. That doesn't make any sense. So they're both going to be attached to 1 carbon, and they're symmetric, right? So we've got that bit. Now, what's their multiplicity? Singlet, right? So can I have any hydrogens on this carbon here? No, right? Otherwise I would have a neighbor, and I would have splitting into a double. So we're going to start drawing bonds out here. One of these obviously has to be carbon. This one might be chlorine here, so let's not fill that in yet. It would be a tertiary chloride. Okay, so now we need to move on a little bit, and perhaps we want to start thinking about the degree of unsaturation here. We've got 1 degree of unsaturation. We've got a signal at 5.3 and 5.1 ppm. What type of hybridization are those carbons? 5.3 and 5.1 in the proton. Above 5 must be sp2. So we've got 2 separate hydrogens on sp2 hybridized carbons. So there's a fragment that gives me that. Yeah? Okay. So we're going to start piecing the fragments together in just a minute. All right, so let's have a look at those hydrogens. One of them, the one at 5.3, is a doublet of quartets, right? So let's call this 5.3. How many neighbors does it have to this side? 1, right? Yeah? So that is the doublet part of the doublet of quartets. 1 neighbor. How many neighbors do we have to get the quartet part now? 3, right? So what has to be attached on here? A methyl group, right? Yeah? How are we doing? Everybody with us so far? This is quite a complicated one. So we've got 3 protons in the methyl group. So that now can't be the methyl group at 1.0. So that has to be the 3 proton signal at 2.0. So this is delta 2.0, and that, it tells you, is a doublet. That's right, because if I sit on this methyl group, I have 1 neighbor, it's got to be a doublet. So I've got a propenyl group, I've got 2 methyl groups attached to what must be a quaternary carbon, and I've got a chlorine. Any other bits? Ah, yes, 3.